All right, how's it going? Welcome back to another video here in the series on mechanics and relativity. We are still in the section here on systems of particles, and we've been going through that for a little while now. And the last video was kind of an interesting case of looking at a system of particles, where specifically one of the particles in our system had a mass which changed with time. It was no longer constant, right? And it's kind of interesting. There are a few types of scenarios where that could occur. We discussed one of them in the case where we have a rocket, right? And that's kind of what we drew right here, where both the rocket's velocity is a function of time, and that kind of makes sense, right? But we also said that the rocket's mass was a function of time. And the idea behind it is that the rocket is losing mass over time because fuel is being ejected out the back of the rocket at some velocity u. So it's progressively losing mass over time. And what we did in the last video was we looked at the system and we ended up deriving the equation of motion for the rocket, which was known as the Tsiolkovsky rocket equation. But the main sort of goal of the last video is not to specifically look at rockets, as fun as rockets are, but rather to talk about how we handle systems where the mass is varying over time, right? And we actually talked about that at the beginning before really mentioning anything with rockets. The main takeaway is that we still want to use Newton's second law for the equation of motion for a system. That hasn't changed in the realm of Newtonian mechanics. But we want to make sure that if we're working with a problem where the mass is varying, right? And it's honestly probably just a good sort of rule of thumb to work with this form of Newton's second law in general. We want to be working with sort of what we call the more general form of Newton's second law, where we write the left-hand side of this equation as the time derivative of the momentum as opposed to the mass times the acceleration, right? Because we saw that the equation F equals ma is only true when your mass is constant. Whereas if you use this equation, you set the time derivative of the momentum equal to the force. The momentum is just mass times velocity. And then you can just plug in your mass as a function of time and velocity as a function of time. Or just assume that both are functions of time and then work from there, right? So anyways, that was really kind of the big thing that we want to take away from the last video. Now, in this video, what we're going to be doing is we're going to be looking at another set of, or I guess another system of particles. And this is going to be another interesting system that is honestly probably quite a bit more common than the changing mass or the variable mass type system. It is known as a rigid body, and working with analyzing rigid bodies. Okay. Now, this video is you can probably tell by the title, it's going to be the first of at least a couple videos on rigid bodies. So our goal here in this video is just to introduce rigid bodies before really diving into things. So I'd say the video probably has two main goals. The first is to look at just what a rigid body is. So when we say a rigid body, what are we talking about? It's the first goal. And then the second goal is going to be introducing some other physical quantities that are going to be really useful for analyzing rigid bodies that we haven't, I guess, explicitly introduced yet. Okay. So that's going to be the goals for the video, and hopefully that makes sense. To start things off, I think it makes sense that in a video introducing rigid bodies, we first address the question of, well, what is a rigid body, right? So I'm going to erase the board. We're going to write out the definition for a rigid body, and then we're going to go from there. All right, so we have the definition for a rigid body right here. So let's go through it together. It says here that a rigid body is an extended object which consists of n particles, such that the distance between any pair of particles, which we can write as the magnitude of the position of particle I minus the position of particle j, so the relative distance between each other stays fixed. So let's unpack this to make sure that we understand what this is, right? Because we're going to be talking about rigid bodies for the next couple of videos. Up until this point in the video series, we have been thinking of anything that has mass as just a point particle, right? We've been saying, okay, if we have an object, we can denote that object like this, and that's its mass, right? And I guess I should be maybe a bit more clear. Even if we aren't thinking of an object like a point particle, just like for instance in the last video where we were quite literally drawing out rockets, right? Even in that case, we were still mathematically treating that object that has mass as a point particle. What I mean by that is whatever our object is, we said that that object just has a single position, could be represented by a position vector x, but the object has a single position denoted by a position vector, and the position vector just pointed to the location of the center of mass, right? And we've talked about the center of mass and how if you have just some object, you could find its center of mass and say that is the position of that overall object, right? So what I guess I really mean is mathematically we've been treating everything as if it's a point particle. But what they're saying in this definition here is that a rigid body is not a point particle, but rather it is an extended object. So there are a couple key features that are going to distinguish a rigid body from just any object that we can think of as a point particle. One of them is that mathematically rigid bodies have more than just one. You cannot just specify a rigid body entirely by one position vector. A rigid body is going to consist of n different particles. Each of those particles are going to have their own position vector associated with them. So it extends beyond just the point particle like structure that we've been defining for objects so far. So if I were to just draw out an example for a rigid body, let's do that. Maybe let's say that I have, I don't know, just make something up like this. I don't know, just kind of drawing things, right? In this case, this would be 5 different particles, and each of these particles will have their own masses. So M1, M2, M3, M4, and M5. Also, each of these particles are going to have their own positions, right? So we have position X1, X2, X3, X4, X5. Okay. Now, I should mention too that these are not nodes and vertices like we're doing graph theory or anything, but these are supposed to be 5 different point particles. But in addition to just drawing the point particles, we also drew out purposefully sort of lines connecting varying particles. It doesn't matter which way I drew the line. I drew the lines. I could have also just added another one like this. That wouldn't have changed anything. But I drew these lines between the point particles for a couple reasons. The first reason is to sort of emphasize the fact that even though we're working with 5 particles, and I guess in the general case we're going to have n of them, but in this example we have 5 particles, these 5 particles make up an overall object, an overall body, which is why we can think of a rigid body as something that is extended, right? This whole thing is the quantity that we are studying, as opposed to just saying the center of mass is, I don't know, maybe there, and that's the object. So that's one of the reasons, to show that we're working with a single overall object. But the other reason is to kind of get an intuitive understanding of maybe how we can think of rigid bodies. I did my best to draw these lines as straight, and I want us for a second to just sort of try to visually imagine that these lines are very stiff, like they're sort of these steel rods. I guess you could bend steel, but imagine that the lines connecting our point particles in our system, imagine that they don't bend. So you can't rotate any of these at all. You can't rotate an individual one without rotating the entire system. These lines are going to remain fixed in place. And that's where the term rigid body comes into play. An example of something that would not be a rigid body is if let's say that all of these lines have to remain fixed, but maybe this line right here is a spring, and you could oscillate the spring back and forth. If this were a spring, then if even just one of these lines were a spring, then this would not be considered a rigid body. And understanding why gets into the second sort of defining property of rigid bodies. The first one being that mathematically we're not just thinking of this object as having one position. That's kind of the first property. The second property has to do with the remainder of the definition, right? Rigid body, it's an extended object, like what we're seeing right here, consisting of some number of particles, but such that the distance between any pair of particles, xi minus xj, is fixed. So if this line right here happened to be a spring that could oscillate back and forth, what that would mean then is that the distance between particle 1 and particle 2 would be able to oscillate, and then this distance would be able to change. But for rigid bodies, this distance must remain fixed. And conceptually, we can think of that as these lines are all stiff. They're not allowed to move. That kind of forces each of these point particles into a set location, and then they're stuck like that, okay? So hopefully that makes sense. Now, I guess we might be wondering, like, what does this apply to, right? With this visual, intuitive picture, it almost just looks like a kid's sort of arts and crafts project, right? You have like maybe cotton balls and toothpicks, and you're sort of making some interesting sort of structure out of the thing. But what does this actually apply to, right? Why is this useful? Why should we care about thinking of rigid bodies? And it turns out that rigid bodies are actually significantly more common than we might initially think. For example, I could say that this pen is a rigid body. And in the sense that it's a rigid body, this pen is made up of a bunch of different atoms if you were to really zoom in on it, right? And of course the atoms aren't exactly frozen. Of course the atoms within here are going to be moving in some way, shape, or form if you want to get really technical with it. But the basic idea is that if we're looking at this marker right here, there are particles on the left end of the marker, there are particles on the right end of the marker. Right now, the distance between the particles on the left end and the particles on the right end make up a distance of about this right here, like what I just made with my fingers, right? Now, if I were to throw this marker in the air, do something like this, almost caught it, something like that, right? While the marker is moving, notice that while it's rotating, I can throw it up in the air, it can slow down, it can speed back up, it can rotate, it can do whatever it wants, but the distance between the particles on the left end and the particles on the right end are going to remain the same. This distance does not change, okay? So you could think of this object as a rigid body. And so really when we're talking about rigid bodies, we're talking about any object whose size isn't sort of transforming during some event, right? Now you could also say, well, can't the tip of the pen come off? Now the distance between here and here is different. So if I were to take the pen cap off, this would no longer be considered a rigid body. But oftentimes, maybe problems that we're working with, maybe we're not interested in taking cap off. Maybe we're just interested in looking at this as some extended object, some object that has more than one position. We want to be a little bit more precise and not just say that its position is at the center of mass, but rather to say that its center of mass is here, but it also has mass here, 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 all the way through here, and over to the other side, okay? So really any object which is not transforming, we can think of as a rigid body. And it's really kind of just a more precise way of classifying objects, certain objects, right? Ones which don't transform. Springs would not be an instance of rigid bodies, right? But yeah, so hopefully that makes sense. That is kind of the general idea behind a rigid body, and you can probably imagine if you just look around wherever you are in your room There are objects which are not going to transform their shape over the course of an event, and hence they can be treated as a rigid body as well. So what we're going to do next, assuming that makes sense, is in this example where I kind of just threw the pen up and let it rotate a bit, the pen was, well, it was doing two things. It was both moving up and down, but it was also rotating. And when talking about rigid bodies, if we imagine rotating this object, even if the object itself doesn't translate at all, even if it remained fixed right here and just rotated, that object would have some velocity associated with it. That velocity is called an angular velocity. And we haven't talked a whole lot about angular velocities. I think we might have hinted at it once or twice before. We've only talked about an object's linear velocity. So what we're going to do next, and this is going to be a fundamental quantity that gets used when talking about rigid bodies, is we're going to talk about the angular velocity of an object and go from there. All right, so rather than write out something, I just drew out a picture that I think is going to be helpful in understanding the angular velocity. Now, a rigid body, in the general case, is going to have n different particles with it, but n could also equal 1. And in the case where n equals 1, then a rigid body just becomes a point particle, right? So a rigid body, in a sense, is almost a generalization of a point particle. Now, what we have right here is just one particle, that's this dot right here. And to explain what's going on, well, first we have an XYZ plane, so we're working in 3 dimensions. And this particle, for whatever reason, decides that it's moving in a circle. So this circle right here denotes the path that this particle is traveling on. I guess it's going counterclockwise in this case, denoted by that arrow. Now, in addition to that, I drew out the spherical coordinates for this particle. So we have r, which is the distance from the origin to the particle's location. We have this angle theta right here, and then also this angle phi. The one additional variable that gets introduced right here is this distance d. That's just going to be the radius of the circle, the distance from the origin out to any point on where the circle is, but projected into the xy plane. So just another way of saying that d is the radius of the circle here. Okay. Now, what we can do is we can come up with expressions for both this particle's position and its velocity. To start with the particle's position, I'm going to write the position vector x. And I want us to just sort of make note of a couple things before we write out the position of this particle. We could, of course, write out the particle's position in spherical coordinates. There's nothing wrong with doing that. But I want us to be aware of which coordinates are changing with time versus which coordinates are remaining fixed. There are 3 coordinates in spherical coordinates, r, theta, and phi, right? If this particle is just moving on this circle right here, the circle's not moving up and down, the circle's not oriented at some angle, the circle is supposed to be parallel. The plane of the circle should be parallel to the xy plane. That's the intention with the drawing here. So in that case, as the particle moves around the circle, its distance from the origin is not changing. This distance r here is going to be computed maybe here, and then at a later point here, at a later point here, and it's going to, as the particle travels along the circle, you would keep computing r. But given that the plane of the circle is parallel to the xy plane, this radial distance, the particle's distance from the origin, does not change. So r is a fixed variable in this specific case. As for theta, this variable right here, as the particle sweeps out, or as it kind of moves along the circle, theta naturally is going to change, right? When the particle is, I guess, right here, it might be 0. It's supposed to be maybe about here, it's pi over 2, here it's pi, 3 pi over 2, and 2 pi, and theta is going to be a changing variable. So we're going to want to write our position in terms of this theta variable. And then finally, what about phi, right? this angle between the vertical and where our particle is located. And that would be kind of the same thing, right? Because our circle isn't changing size, the circle isn't shrinking at all, it's not getting bigger, it's just a constant circle. So phi, this angle from here out to wherever the particle is located, that is going to be constant as well. So interestingly, even though this is a problem in 3 dimensions, only one of the coordinates actually changes with time. And I guess hopefully that makes sense, right? A circle is just a type of closed curve, and curves can be parameterized by one variable. So the point of saying all of that is that we're going to want to write first the position just in terms of the variable which is actually changing. Okay. So for the x position, if this is the angle theta, then the way to get the x component of its position is to take the radius of the circle, d, times the cosine of that angle. Right, the cosine is going to give you this component. So the x component of our particle is d times cosine theta. And again, just to make sure we're clear, d is a constant too, right? If the circle's not changing in size, then the radius is the same. As for the y component, we just take the sine of that angle, and then we're going to get the same thing. So we have d cosine theta, d sine theta. And then for the z position, I guess that the way that we'd actually write this in terms of spherical coordinates is to say that we'd have r times cosine of phi, right? But r and phi are both constants. So maybe what we could do is we could just make up some fixed height that the circle exists at h. Say that h is just r cosine phi, right? Oh, there's my eraser. R cosine phi. And then say that the particle's z position is h. So it's expressed in terms of constants, d and h, and then the theta variable. So this is the particle's position. What we could do next is we could take the particle's velocity, which is just taking the time derivative of the position, right? For the x component, that would just simply become negative d sine theta, theta dot, because again, theta is the only thing changing with time. For the y component, we're going to have d cosine theta times theta dot, like that. And then for the z component, we're just going to get 0 because h is a constant, right? So we have the coordinates for x and x dot, and it turns out that I think it's probably easiest if you can either take my word for it, or what I'd recommend doing, not take my word for it, and just try it yourself. But it turns out that both this vector right here, this is just a 3-component vector, and this vector can be related to each other through a given cross product, okay? And the relation between these two vectors is as follows, or we could write that the velocity of the particle is going to equal a cross product. One of the inputs to the cross product is the position vector. The other, in the first input, is this additional vector omega, okay? And it turns out that omega is the angular velocity of this particle. All right. So maybe we'll say that this thing is the angular velocity of the particle. Now, to actually relate these two, we can actually find out what omega would need to equal, just for I guess, to not just do too much laborious math. I'm just going to tell you what it equals. Omega, as a vector, is going to equal theta dot in the z hat direction. Or I guess if I'm going to write it out component form like this, omega is going to equal 0, 0, theta dot. Okay. So this is the angular velocity of this particle right here. So I guess just to try to get an intuitive understanding of what the angular velocity is, I think it's conveniently named. In other words, the term angular velocity describes it quite well. If we were to look at the magnitude of, this is a vector, right? Maybe that's the very first thing. Angular velocity is a vector quantity. The magnitude of this vector is simply theta dot. So the magnitude of the angular velocity talks about how fast this particle rotates. And I think that kind of makes sense, right? If we're talking about velocity, it's how fast is something going. And angular velocity is how fast are you just moving in an angular motion? How fast are you rotating, right? And then, so that's the magnitude. In terms of the direction associated with the angular velocity, notice that both of these components here is 0. They're not going to be 0 in the general case, it's just for this specific problem. But in this specific problem, omega only has a z component to it. If we look at our diagram right here, our circle, again, is parallel to the xy plane. So the direction that is normal to this circle points in the z direction. And it turns out that is the general trend, that the direction of the angular velocity vector is always going to point perpendicular to the plane defined by the area of your circle. Okay? So to maybe just not put so many words on that, if I had a circle that's off at some angle, the angular velocity vector would point perpendicular to that. Okay. So hopefully that makes sense. And if that makes sense, again, this just in describing the angular velocity, what we've done so far has been for one particle. This is going to generalize for some general rigid body, where I'm just going to draw out a quick rigid body, I don't know, down here. Maybe we have 3 particles. They're all connected. And what we could do then is we could define some axis that this object rotates about. All right. I'm going to specify that axis with a dashed line. Maybe I'll do it here. The line is arbitrary. I purposely am not. That's not meant to be a straight line. I'm meaning to draw it at an angle. And if this rigid body, the terminology that we would use is that if this rigid body is rotating about this specified axis right here, then hopefully we can see that each of these particles that make up the rigid body are just going to rotate in circles about this axis right here. And I'll draw it out. So if this body is rotating specifically about this axis, then this particle will make a circle that looks something like this. This particle is going to make a circle that looks something like this. This particle is going to make a larger circle. I guess that's getting kind of messy at that point. But hopefully you can see that just each of these particles' distance from this axis defines the radius of their respective circle that they're traveling in as they rotate about that axis. I feel like that's a lot of words, right? But hopefully that picture makes sense. Now, I think one of the natural questions somebody could have is, well, this is the angular velocity for a particle moving in a circle, right? Well, what if the particle isn't moving in a circle? and that's a perfectly good question to ask. What if the particle is not moving in a perfect circle? In that instance, what we would say is that the particle does not just have a rotational motion associated with it, but it also has a translational motion. And we're going to get to that in a future video where we kind of generalize how a body is moving if it is both moving in the translational direction as well as the rotational direction. But what we're considering right now, and when talking about the angular velocity, you're simply talking about the rotational motion of an object. And hopefully the picture, as messy as this is somewhat clear here, because if we have this object that consists, this rigid body that consists of 3 particles, if we're only looking at its rotational motion, so not how it's kind of buzzing around in space, but just that it's rotating about this axis defined right here, then hopefully we can see that each of the paths of these particles are going to make circles about the axis of rotation. Okay. So it's a good thing to be thinking about. What if the trajectory of these particles are not just circles, but that sort of combines multiple types of motion, and we're just going to sort of stay focused on rotational motion for now and talking about the angular velocity. So hopefully that makes sense. This vector omega is going to be something that's going to show up a lot and at least what we're going to do next is we're going to erase the board, and we're going to show how some of the quantities that we're already kind of familiar with, whether we're talking about an energy of a system, a momentum associated with a system, how we can incorporate this new vector, the omega vector, the angular velocity vector, how we can incorporate that into those definitions. Because we're gonna see that when we do that, some interesting properties are going to emerge, and a whole discussion is going to go from there. Okay, so what we've drawn out here, again, is just sort of some general picture for a rigid body, but there's nothing special about a rigid body with 5 particles. I could have drawn as many as we want. What we're going to start to do now, and what we're going to do for the remainder of the video, is we're going to see how that angular velocity vector omega fits into some of these other generalized quantities, or I should say these other quantities that we're already familiar with. The first thing that I want to do, though, or I guess a couple of things I want to do before we dive into that, is to see how the definition that we had in the previous whiteboard, where we related the linear velocity x dot to the angular velocity omega through this definition right here, how does this generalize when going from one particle to a system of potentially n different particles, right? And the way that this generalizes is that now that we have n of these particles, each of these particles is going to have their own linear velocity with them. So I would have to put a subscript I when we're talking about the ith particle. And naturally, if each particle has its own velocity, it's going to have its own position vector too. So we're going to put a subscript I there. But we're going to stop with the subscripts. There's not going to be any subscript on the omega vector, which might seem interesting or peculiar, but hopefully this makes sense once we take a little time to think about this. It turns out that if you have a rigid body that has an associated angular velocity omega, then that angular velocity is going to be it's the angular velocity of the rigid body, and that's going to be the same angular velocity for each of the point particles in your rigid body. And let's maybe try to understand why that's the case. If I have an axis of rotation right here, it's supposed to be a straight line, something like that, and my rigid body is rotating about this axis, right? Hopefully it makes sense that whether I'm talking about particle 1 or particle 5, if the rigid body starts here and then it rotates around the axis, makes a full rotation and gets back to its starting point, then by the time M1 gets back to its starting point, by definition, M5 also needs to get back to its same starting point. It's true that M5 will have had to cover more distance than M1, right? So hence, if you're going to cover more distance in the same amount of time, you're going to be moving faster. So each particle is going to have a different position and different linear velocity. But the rotational velocity, the angular velocity that the system rotates at, is going to be the same for each particle. And this is something that's kind of nice about working with rigid bodies and their angular velocity, is that really all you need to do, if you wanted to find the angular velocity of a rigid body, you don't need to calculate it 5 different times or n different times. You can just pick a particle, calculate its angular velocity, and then that's the angular velocity for the system. Okay. So that's kind of one of the generalizing properties about this omega vector, is that as long as you're working with a rigid body, then omega is going to be the same for a system. Just to make sure we're absolutely clear on this, if your body is not a rigid body, so now the distance between these particles is allowed to kind of oscillate and the whole system's maybe jiggling, now each of these particles is going to have their own angular velocities. So this property that we don't need a subscript here is specific to rigid bodies. Okay, that's the first thing I want to make sure we're clear on. The second thing is just to show that with this definition right here of relating the linear and angular velocity vectors, it upholds the natural property of rigid bodies. And the natural property of rigid bodies, what I mean by that, is that if I were to take the time derivative of the relative position between any two particles, so absolute magnitude of xi minus xj, take its time derivative, if this quantity is really fixed, right, then the time derivative should go to 0. So we're going to just show that really quickly. I think that can be helpful to show that rigid bodies, the definition doesn't break down with this relationship right here. So this time derivative, I'm actually going to take the square of it, because if the square distance goes to 0, then so does the distance itself, right? And by writing out the square distance, we can apply a chain rule to get 2 times, I guess this would be xi minus xj, and a dot product with, so this is like chain rule. You have 2 times the quantity, and then you apply chain rule to the inside part. So then you have x dot I minus x dot j, like this. That's how we can express the time derivative. And then what we're going to do is we're just going to rewrite x dot I and x dot j in terms of this definition right here. So this is 2 times xi minus xj in a dot product with this first one is going to be, I guess, omega cross xi minus omega cross xj, right? Now this can get simplified into just omega cross xi minus xj. That's just a vector identity, right? So we have 2 times xi minus xj in a dot product with omega cross this input minus this input, so xi minus xj, like this. Okay. And I think at this point, now we can kind of see why this thing must go to 0. We know that the cross product takes in 2 vectors as inputs, and it outputs a vector that is perpendicular to both of the input vectors. So crucially, whatever this output vector is that's in this large set of parentheses right here, it's going to be perpendicular to xi minus xj. And then if you dot whatever the resulting vector is here with xi minus xj, you're going to get 0, right? So this whole quantity just goes to 0. And that's nice, right? Because how we define our angular velocity in relation to the linear velocity, that should still allow for rigid bodies to exist, right? So hopefully that makes sense. What I'm going to do right now, I'm just going to, I guess, erase this first result. What we're going to look at next is we're going to look at the sort of kinetic energy that's associated with rotating this rigid body and incorporate the omega vector into that definition. Okay, so the first thing that we're going to do is we're going to look at the total kinetic energy associated with this rigid body. Now, I want to make sure before we dive into this, I want to make sure that we're understanding what is this the kinetic energy of. So in order to have kinetic energy, you need to be moving, meaning your velocity needs to be non-zero, right? So this rigid body is moving in some way, shape, or form. But I want to make sure we're clear on how is the rigid body moving, right? There are many different ways which we could define the velocity of the ith particle in the rigid body. But what we're going to do is we're going to say that the velocity of the rigid body is given by this expression right here, by the definition that relates the linear and the angular velocity. So with this definition, the type of motion that corresponds to is if the rigid body is just sort of rotating about an axis, okay? So in other words, each of these particles are going to sweep out circles of different radii as it rotates around this axis. So when we're referring to kinetic energy, what we're really referring to is the rotational kinetic energy associated with this object. In the more general case, when not only is this object rotating, but it's also kind of moving, it's translating, the total kinetic energy would be the sum of both its translational and rotational kinetic energy. So what we're really doing here is just the rotational part. So I'm going to include rotational into here. But this is still going to be our starting point, okay? So this is the total, I guess, rotational kinetic energy. First step, just like what we did prior, is we're just going to substitute in the definition for x dot in terms of the omega vector. So if we do that, we're going to get 1/2 times the sum over I mi, and then our first velocity vector is going to be omega cross the ith position, and that's going to be in a dot product with itself, right? Omega cross the ith position. Okay. Now at this point, this is kind of a generalized vector identity. This is almost A cross B dot C cross D. So I'm just going to write that out maybe over there so we have the generalized vector identity at our disposal, and then we're going to be able to simplify it a little bit more from there. All right, so this is just an identity from vector calculus. I certainly don't memorize it, but it turns out that A cross B dot C cross D is the quantity A dot C times B dot D minus A dot D times B dot C. All right. So we're just going to incorporate that definition into here to get to the next line. And we're going to get that we have 1/2 sum over I, still the mass of the ith particle, that's out front. I'm going to put a big set of brackets kind of around everything, where the brackets is going to just rewrite this dot product of cross products using this identity right here. So A dot C is, I guess, the omega vector, its magnitude squared. When I'm writing, by the way, omega squared, I mean the magnitude of omega squared or omega dot omega, or however you want to think about it, but that's what I mean when I'm writing this. That's A dot C. B dot D is going to be xi squared minus A dot D omega dot xi times B dot C, which is xi dot omega. We're working with real valued vectors, so the dot product is symmetric. So I can just write, I guess, omega dot xi, this quantity squared right here. Okay. So that's just implementing the vector identity. It turns out there's going to be one more sort of property from vector calculus that we're going to want to make use of. And it talks about how you can use vectors to define the perpendicular distance from an object's location to a given axis. That sounds general, or that might sound confusing right now. I'm going to just write out that identity down here. I'll explain what it means, and then we're going to sort of be able to, I think that should be all the tools we need then to finish off simplifying this expression at that point. Okay, so what we just, this is another relationship from vector calculus. But what this quantity describes, which we're going to call little d sub I, and I want to make sure that we're clear on what is what here. So d sub I it's a scalar quantity. This is not a this is not a vector. I'm purposely not writing a vector sign over this. This is not the ith component of a vector, but rather what is the distance from the ith particle, or specifically the perpendicular distance from the ith particle to the n hat axis. So because this is a scalar quantity, it's given with absolute magnitude signs. So we're taking the magnitude of a given vector quantity. I just want to make sure we understand what this conceptually represents though, okay? So when we're saying the n hat axis, we're gonna see how that relates to things in a second. But for now, just take the n hat axis to be this axis, the axis that we're rotating around, okay? So n hat is pointing in the positive, I guess the z hat or the k hat direction, it's pointing upwards. And if we wanted to find this quantity d sub I, what we are inherently finding is the distance from a given particle, maybe d3 is the distance from this particle to the axis. But you would say the distance from this particle to what point on the axis, right? You can say the distance from the particle to here, the distance to here, the distance to here. Well, it's the distance such that if we were to draw a line from the particle to the axis, it would make they would be perpendicular to each other. So we could draw a distance from here to this point on the axis, and at that point they make a right angle, and that is how d sub I is defined, as this scalar distance right here. Okay, so that's what that represents. We might be like, where are we going with this? We're going to tie all this together in a second. For now, though, I just want to manipulate this expression just a little bit, and again, we'll see how this connects. Where do I have room for this? Maybe I'll do this up. No, I think I can do this down here. So if I were to take the square of this quantity, I would get di squared, and that would just be this, the magnitude squared, or this vector quantity that's inside absolute magnitudes, that vector in a dot product with itself, right? So what I'm going to write it as Ri minus n hat dot Ri n hat in a dot product with itself. So Ri minus, I probably could have sped through this part too, but whatever. Ri n hat. Okay. I need an I there. Looks right. So now let's just evaluate the dot product. We first have Ri dotted with Ri, giving us Ri squared. Then we have Ri dotted with this quantity. That's going to be n dot r. I'm just going to say n dot r, and then we have r dot n. So n dot r squared. But we're also going to get the same thing when we take this in a dot product with this. So we're going to have two of those factors, right? We're going to have minus 2 n dot r squared, like that. And then our final term is this term in a dot product with this term. The negatives are going to cancel, so we have a plus sign. Then we have n dot r, another factor of n dot r, so n dot r squared. N dot r squared. And then we have the vectors themselves, right? We have n dot n. But n dot n, these are, n hat is a unit vector. The hat indicates it's a unit vector. So we know that n dot n needs to equal 1. So it's just like writing the number 1 right there. So this is what we end up getting when we take the square of this distance right here. And notice that we have something minus 2 times this quantity plus that same quantity. These two can simplify into just the negative of this quantity. So this is, and hopefully we can still see it down here. I wanted to keep it on the left side of the board, so we had the right side for the actual rotational kinetic energy. But this is just n hat dot Ri times n hat dot Ri, like this, okay? That is the square of this distance d sub I, all right? Now the reason that I wanted to evaluate this quantity squared here is because if we look at this expression, right, and then we turn our attention over here to the expression in brackets, they look very, very similar, right? And the final way that we can connect this is that if we're assuming that the angular velocity is constant, in other words, there's no angular acceleration involved, then what we can do is we can say that the angular velocity vector is the magnitude. This is a vector, it has a magnitude, which we can just call omega without the arrow, right? So this is its magnitude, and it points in the n hat direction. And that's how we're going to think of the omega vector, okay? So if we were to think of the omega vector in this way right here, right? Hopefully, can we see that if we were to take the magnitude of omega, just the scalar quantity omega, and square it, multiply it by di squared, so now we're getting omega squared di squared. Let me even write it just so we're not just saying stuff. Omega squared di squared. How is that going to change this expression, right? Well, I multiplied omega squared on the left. I need to multiply omega squared now on the right. So that's going to multiply into the first term. like that. And then if I multiply omega squared into this second term, one of those omegas can go for this vector into this n hat vector. One of those omega factors goes into this n hat vector. So I can, if I multiply both sides by omega squared, I can replace the n hats with the omega vector. And now notice that omega squared di squared is exactly what we have here in brackets. So all of that is to say, if we're able to follow that, all of that is to say that the rotational kinetic energy for a rigid body is going to be 1/2 sum over I mi, and then rather than the thing in brackets, which is a scalar quantity, I'm just going to replace that with omega squared di squared. Omega squared di squared. Or again, this is simply just the magnitude of the omega vector. All right. Hopefully that made sense. That's kind of the way that all of this ties in together. Now, we're not quite done. I guess we're pretty much done in the sense that we've defined our rotational kinetic energy in terms of the omega vector, or its magnitude. But what we're going to do is we're going to do one more thing. And we're going to make use of the fact that the omega vector, and therefore its magnitude, is going to be constant for each particle. It doesn't have a subscript I for a reason, so we can pull it out of the summation. And if we do that, we're going to get 1/2 omega squared out in front, and then we have our sum over I mi di squared like this. And I'm going to just define, for now, a mysterious quantity that will remain mysterious for now, called capital I. And capital I is going to be defined to be the sum over I of mi di squared. Okay. Now, why are we doing this? Well, there's a couple reasons why we're doing this, but the main thing that I want us to see, at least for now, we're going to get into what all this is eventually. But for now, if we define some quantity to be called uppercase I, and we define it in this way, then the total rotational kinetic energy becomes 1/2. This whole thing with the whole summation, we're just calling big I. And then we have omega squared. Okay. This is our expression for the rotational kinetic energy of the rigid body. So it's kind of interesting, right? Because we normally think of the kinetic energy as, up until this point, it's always just been, it's 1/2 mv squared, right? Now we're getting something that's 1/2 I omega squared. We don't have the linear velocity v, we have the angular velocity omega. And we don't have the mass, but we have this thing, I. Okay. What we're going to do next is we're going to erase the board. We're going to look at how we can also define the total angular momentum of the system, well, in terms of the omega vector. And that will kind of be the stopping point, at least for this video. All right, so we've summarized the results that we've gotten so far, kind of up here. Right, so we're starting with our relation between the linear and angular velocity, talking about how we're defining the angular velocity, just assuming it to be this constant angular velocity. There's no angular acceleration. And then finally, what we just came up with, an expression for the rotational kinetic energy of the system being 1/2 I omega squared, where this is our definition for I. To finish off the video, we're going to talk about the total angular momentum of the system. Kind of funnily enough, right, we've already talked about an angular quantity being angular momentum, and we've needed to do that really to talk about conservation laws, right? So because we have conservation of energy, momentum, and angular momentum. So we want to see, our main goal here is to see how is this angular momentum vector defined in terms of the angular velocity vector, the omega vector. This is the definition for the angular velocity, and then I just rewrote p sub I, the linear momentum, as the mass times the linear velocity, right? So that's all we've done up until this point. What we're going to do is similar to what we've already done in couple times now, where we're just going to replace x dot I with the definition and its relation in terms of the omega vector. So I'm going to write this as sum over I. We have the ith mass times xi. Maybe I'll put brackets here too, just to maybe make it a little easier to read. We have xi and a cross product with x dot I, but that's this quantity, right? So that's omega cross xi, like this. Okay? Now, what we're going to do is sort of one further step, at least for now, is we're going to, well, first, I guess, use the fact that we're going to assume our angular velocity is constant. So we can write the omega vector as omega n hat. And again, because this is the same for each particle, this scalar quantity omega doesn't depend on I, so it can be brought out to the front. So I can write this as omega times the sum over I, mi, and then the same thing in brackets, right? Or pretty much the same thing. Xi cross. Now instead of omega, we took the magnitude out, so we're left over with just n hat cross xi like this. So that's what the expression would be. And I'm going to do one more thing here, where I'm going to take both sides of the equation and I'm going to dot it with the n hat vector. Okay? So we're not exactly looking at the angular momentum, but we're looking at the angular momentum projected along the direction specified by the axis of rotation. So L dot n hat. This whole thing is L, so if I'm dotting it with n hat, I'm just taking n hat like this. Okay. So this is what we have so far. Now, just like before, where we're going to need to make use of a vector identity, I'm just going to, I don't remember it off the top of my head, when you have a vector cross a cross product. So I'm going to write out that vector identity right here. We're going to simplify that a little bit, and then that'll be able to allow us to simplify this expression. Okay, so this is the general vector identity where we have A cross the quantity B cross C is A dot C times B minus A dot B times C. So we're just going to apply that vector identity to what we have in brackets right here. So if we do that, we're still going to have omega out front times our sum over I times the ith mass. And then I guess I'll keep it in brackets. Rather than this identity, that's what we're going to have. So our first term is A dot C, so x quantity squared. So we're going to have xi quantity squared times B, which is this. So xi squared times n hat as my first term. Hopefully we see that. Minus A dot B. A dot B is xi dot n hat. Xi dot n hat times the vector C, which is xi. Right. That is the term in brackets, and then we're still dotting that with the n hat vector, like this. Okay. Now, what we can do is we have one vector minus another in a dot product with the n hat. We're just going to distribute that in and see how that simplifies. So we're going to get omega times the sum over I times the ith mass, and then if I distribute n hat into this first term, I get xi squared times n hat dot n hat. But what is n hat dotted with itself? Well, it's just going to be the number 1, right? Because it's a unit vector. So this is just going to be xi squared minus xi dot n times xi dot n, or just xi dot n quantity squared. Xi dot n hat quantity squared. Now, I probably should have kept this definition up, but hopefully, do we remember from the previous whiteboard that this expression that we have here in brackets is the quantity di squared? Like if we just go back a whiteboard, this is what that would equal, right? So because this is di squared, I'm just going to replace the bracket term with di squared. And what we see is that we're going to get omega times the sum over I times the ith mass times di squared, right? But we had a name for this sum over I of the ith mass times di squared. That was our definition for this quantity big I. So we can rewrite this as simply I, big I, times omega. All right. And that is, I guess, the result that is worth boxing. So to add on to our list of results here, this is the rotational kinetic energy, 1/2 I omega squared, and now the nth component, or the normal component, well, let me say that again. The component of the angular velocity that is along the direction of, along the axis of rotation is I omega. Okay. So interestingly, this I quantity shows up in both of these things. To finish off the video here, I just want to comment on this because this is kind of interesting, right? This is the rotational kinetic energy. The normal translational kinetic energy is 1/2 mv squared. The rotational one is 1/2 I omega squared. The linear momentum, normal, just standard P, normal momentum is mass times velocity. This component of the angular momentum is I times omega, where instead of the linear velocity, we have the angular velocity. Instead of the mass, we have big I. All right. So it seems that whether it's a coincidence or not, and it's not, this quantity big I seems to show up in these places where mass used to be for the corresponding translational quantity, whether it's energy or momentum or whatever it happens to be. That's not a coincidence. It turns out that big I has a name. It stands for the moment of inertia. And that is going to be a quantity that we're going to talk about quite a bit more. And we'll probably spend the next video just dedicated to talking about the moment of inertia. But this is a subtlety that starts to show up when talking about rotational motion. That will show up significantly when talking about rigid bodies and how rigid bodies rotate. There's this quantity that is not the mass. It's not simply the sum over mi, but it's mass times this corresponding distance, this perpendicular distance from the axis of rotation. Okay. I want to leave it at that point because next video we're going to get into all of that stuff. Okay. But yeah, thank you so much for watching. I'm excited to make this video, excited to make the next video too on moments of inertia. So yeah, well, see you then.